This is Lab 2, Motion of a Falling Object by Caitlin Schmidt.
I investigated the motion of an object dropped from rest. Newton's second law is key to understanding how an object's position changes over time under a net force. The tools I used were the tracker, which analyzed the object's motion over time from the experiment, and GlowScript to make computational models for the predicted motion. And these models involved motion predicted with only the force of gravity, and also motion predicted with the force of gravity as well as drag force. And I observed motion, and I will be comparing the predicted motion as we go on. For the physics principles, I use the position and velocity update equations, which are listed right there. And also I use that version of the position update because the force is now constant. And the forces acting on the paper are gravity and drag, which also includes the variables used for that. The tracker, I set the mass of the paper as 0.005 kilograms, and the paper should experience some drag force. And I want to determine which computational model better represents the paper's motion. The key objective is to analyze if net force consists of only gravity, and drag force, or additional unknown forces. The coordinate system has the origin set where the paper fell, and for the data collection, I recorded the position for that amount of time and for around 0.5 seconds. And I estimated the initial position as that in the y plus direction. For the coding without drag, I enter the paper's mass, the initial position, and the initial velocity, set t equals to 0, set delta t to 0.017 seconds, and created a while loop for while t is less than 0.055 seconds. And I calculated the force of gravity and set it equal to the net force, entered position and velocity update equations, set the arrow positions, the position of the ball, and set arrow axis equal to the force of gravity times the arrow scale. And I also included an example of the code. For the coding with drag, I copied the first code, but I added drag force into the while loop and calculated the most accurate v value through trial and error, so the final y value in the tracker was similar to the one in the code, and created a second arrow for drag force, set all the arrows up, and use the following formulas. I also included a link on my code and a picture. Is the data, I included a graph, and I included a part of the data. The analysis, I concurred that the computational model with gravity and drag force was the most accurate. The model with only gravity predicted a way faster velocity increase since it lacked drag. The model with both forces closely matched the observed motion in the tracker. So the what-ifs of observing the velocity versus time graph for both models shows that neither predicts an end velocity, and the velocity never reaches a constant value. If the paper was dropped from a higher position, the drag force model would be more likely to demonstrate terminal velocity. The gravity-only model cannot predict terminal velocity since no opposing force is present. And the effect of throwing the object downward, the terminal velocity remains the same since the paper did not reach it. Throwing it downward would result in a greater final velocity than just dropping from rest. To stimulate this, an initial velocity of 0.678 was added, and the simulation confirmed the final velocity was greater than the experiment at the same time. Conclusion, selecting the mass point for each interval was challenging, leading to slight inaccuracies. In an ideal real-world scenario, the model including drag force was most accurate since it accounts for the most variables. In a future experiments, using an object that falls slower and experiences stronger drag force could provide better insight into the effect of air resistance.